Okay, so section 4.4 talks about graphing with calculus and calculators. Um, so it says in the intro here that the method we used to sketch curves in the preceding section was a culmination of much of our study of differential calculus. The graph was the final object that we produced. Okay. In this section, our point of view is completely different. Here we start with a graph produced by here we start with a graph. Let me just highlight this. Hold on. Here we start with a graph produced by a calculator, and then we refine it. And then we use calculus to make sure we reveal all important aspects of the curve. So section 4.3 is more fundamental because there you're using calculus to learn about the function and graph the function. In section 4.4, they have more difficult functions and that don't have like nice values for like local maxima, local minima, that sort of thing, or inflection points. And so they use a calculator to help you. That's what they have for section 4.4. So let me show you what let me just like go through an example here. Okay. So of course, my emphasis is on 4.3, but nevertheless, 4.4 is a topic that is supposed to be covered. Let's talk about that a little bit here. So in example 1, they want you to graph this 6th-degree polynomial, and then use the graphs of the first and second derivative to estimate all maximum and minimum points. So this section is really reminiscent. It should remind you of section 2.7, where you looked at graphs of derivative functions, and then based on that, you were able to talk about the function in various ways, the original function. So, all right, 6th-degree polynomial is very difficult to graph. Okay, very difficult to graph. And what they do in figure 1 is they graph. Hold on, let me go back in my book here. I want to have it right in front of me. They go back and graph the function, but you know the function, because it's of a 6th degree, the polynomial is of 6th degree. It rises extremely quickly. And so what they do in figure 2 is they zoom in basically about the origin. Okay, they zoom in about the origin. So if you look at figure 1, you can't see based on that window. You know, you can see that the function, you know, is decreasing and that it increases, but you can't see, for instance, the concavity. You don't know where. I mean, it looks like the function in figure 1 is concave up all the time. Okay, but if you zoom in a little bit near the origin, see how the window changed? It's not from -5 to 5 anymore on the x-axis. It's from -3 to 2. And now, and also the y-axis goes from -50 to 100. And so now you have based on the graph, you have a better idea of the concavity. I mean, clearly the function f of x starts off as concave up, and then it switches to concave down, and then it goes concave up again. Okay, but because the function is a complicated polynomial function, it's of 6th degree. It's not easy to. I mean, like it's one of these problems where. Well, let me show you here. Where's the function increasing and decreasing? Okay, you're gonna take the first derivative, and there's your first derivative. F prime of x equals 12x to the fifth plus 15x to the fourth plus 9x squared minus 4x. And that, you can factor an x out, but when you get with what's left, it's not like it factors nicely. And the same for the second derivative. The second derivative is 60 times x to the fourth plus 60x cubed plus 18x minus 4. The second derivative does not factor nicely. Okay, and so what they say is look at the graphs of the first and second derivative, and those graphs will reinforce the behavior of the original function that you're seeing here in figure 2. So it reminds me of section 2.7, where you looked at derivatives of functions and then tried to match the derivative with the function. So how many recall doing that? How many recall doing that in section 2.7? Problems where you looked at derivatives of functions, and then based on that, you learned about the original function. It's been a while, right? Or match each function with the graph of its derivative. Okay, so yeah, all right, Sebastian remembers, Joe remembers. Let me just see here. I see problems in 2.7 where it says match the function with the graph of its derivative. And then I see problems where you're given a function and you have to graph the derivative. So you've graphed derivatives based on functions. Okay, you've done that, and you know that and Zoe remembers the matching. So all they're doing here is they're saying, look, let's go ahead and graph that first derivative. Okay, that which is a fifth degree polynomial. Let's graph it, and they graph it here in figure 3. And based on the first derivative, you can tell information about your original function. Like, for instance, the first derivative goes from, well, in the picture, it goes from negative to positive. It goes from negative to positive when x is about equal to negative 1.62. They tell you that in the reading, in the paragraph. The graph of the derivative goes from negative to positive at about x equals negative 1.62. So that means then that the function, since before x equals negative 1.62, at least for this interval they're looking at, the function, I want to say this the right way. Hold on, the function's decreasing. The function's decreasing, and then when you reach a value of x equals negative 1.62, the derivative goes positive, and so then the function increases, and then it increases, and it stays increasing because the derivative is positive until you get to about x equals, well, you see that blue function in figure 3, the blue derivative function, dip below the x-axis a little bit. And then it goes, and then the derivative goes above the x-axis and becomes positive. So at x equals negative 1.62, the derivative changes from negative to positive. That means you have a local minimum at about x equals negative 1.62. And then when x is close to the origin, and they're saying it's about negative 0.1, the derivative goes from positive to negative. The derivative goes from positive to negative. And that means, of course, that you have a local minimum. So there, at about x equals negative 0.1. So the function will have a local maximum at about x equals negative 0.62. The function will have a local, I want to say this the right way, the function will have a local minimum at x equals negative 1.62, because the derivative function changes from changes from negative to positive there. In other words, the function's decreasing when the derivative function is negative, and then the function's increasing when the derivative function's positive. So going from the function increases and switches to the function decreases and switches to increasing, you have a local minimum. So you're looking at the derivative, and based on the derivative, you're ascertaining, based on the derivative function, you're ascertaining where the function is increasing and decreasing. And similarly, you can look at the second derivative in figure 5. And based on the second derivative, you can figure out where the function is concave up or concave down. So the second derivative looks to be positive until about negative 1.23. So from negative 1.23, from negative infinity to negative 1.23, this function is concave up. But then the second derivative stays negative, which means the function is concave down until it reaches about 0.19. So from negative 1.23 to 0.19, the function's going to be concave down. And then the function goes, the second derivative becomes positive at 0.19 to infinity. So the function goes back to concave up. And so you see, but you see these decimals, the only way you're going to get these decimal values, negative 1.23, 1.19, the only way you're going to get those is to use like your calculator, the zero function, to find the roots of the function. Okay, nobody's expecting you in section 4.4 to find these decimal values analytically like we did in section 4.3. You're going to use you're going to graph the second derivative function and then use the zero feature on your TI calculator to find out those values. So you're using calculus, but you're also using your calculator to help you in section 4.4. Okay, and that's an example of and the function in figure 2, all its behavior, it decreases until you get to x equals negative 1.62 about, then the function increases, but it decreases a little bit. There's a little dip around negative 0.1, which you can't see in the graph, but it's there if you graph the derivative function. And then the function increases. So, I mean, really, what's involved here is graphing the first and second derivative of the function, and then based on that, finding out where the function increases or decreases and where the function has where it's concave up, concave down. Okay, so basically you're using your calculator in section 4.4 to help you figure those things out, because the functions are too complicated in section 4.4. But you will not do that in section 4.3. In section 4.3, for those problems, those functions are simple enough that you can work off of the charts to determine where functions are increasing and decreasing and where functions are concave up, concave down. So the book, then goes to a rational function here, and they want you to draw the graph of this function. And they make a comment that if you were to just use a computer with automatic scaling, like for instance MATLAB, when you take your 200 level courses, you'll work with computer programming called MATLAB. And MATLAB, if it were to graph this rational function, x squared plus 7x plus 3 over x squared, it would produce a graph like in figure 6, where, at x equals 0, the function basically it's very large, right? That's 3 times 10 to the 18th power in the y window. The y scale, the y-axis goes from 0 to 3 times 10 to the 18th power, and that's the computer's way of saying, hey, there's an asymptote at x equals 0. All right, and so what you have to do is you have to limit your window. You have to limit your window. So if you limit your window to a standard viewing window, you can see much better how the function acts. And you can see that the function starts off, like I'm looking at figure 7 now. I'm looking at figure 7. You can see the function starts to decrease. It's concave down. Or concave down. And then it appears to, it increases, and it appears to be concave up. And then going after x equals 0, the function appears decreasing and concave up. So, you know, to confirm that, you can look at the graph of the first derivative. Okay, you can look at the graph of the first derivative, and you would be able to gather this information. And of course, there are asymptotes. There are asymptotes here, horizontal asymptotes. I want to say this the right way. One moment here. Yeah. How many remember this kind of thing from calculus or pre-calculus, where you find a horizontal asymptote? You did that in pre-calculus, right? You take, so a horizontal asymptote is if the limit of the function as x goes to positive infinity or negative infinity approaches a number, you have a horizontal asymptote, and it's clear y equals 1 is the horizontal asymptote. Okay. And you know, and then they take the first and second derivatives. They take the first and second derivatives. Here's the first derivative of our function. F prime of x will equal negative 7x plus 6 over x cubed. And it shows then that the first derivative is positive when x is between 0 and negative 6/7, and the first derivative is negative when x is less than negative 6/7. So there's really, I mean, you know, really there's, and you could just as easily graph the first derivative. I honestly don't know why they didn't do that. Just graph the first derivative and determine, you know, that the first derivative is positive when x is between negative 6/7 and 0, and the first derivative is negative when x is less than negative 6/7. That would establish that you have a minimum value at x equals negative 6/7. They choose not to do that, but the point is, you're using in section 4.4, you're using graphs of the first and second derivative to help you understand the behavior of the function, and then you'll use your zero function when you graph the first and second derivatives. You have to get a good window, but after you do that, you can find out local maxima, local minima by using, and inflection points using your zero function, zero feature on your calculator. So, you know, really, they get quite complex in section 4.4. Here's and I'm just giving you a guided tour. I mean, there's really not a whole lot more that I can say about section 4.4. I mean, you know, except what I said. I mean, but here's the sine of x plus the sine of 2x. That's example 4. And, you know, they have this figure 15 here, figure 15, where they graph the function, and it's a very interesting function, and they talk about, you know, for this part of the function, you know, the function has concavity that's switching from concave down to concave up. You see that in figure 15, the graph of your function, sine of x plus the sine of 2x, and of course calculators in radian mode. But you see how the function goes concave down, and then concave up, then concave down, and then concave up, and then concave down. How many are noticing that? How many are noticing that in the figure? figure 15. I mean, look at that function, figure 15. You see how the function's concave down, and then it goes to concave up, and then concave down, concave up, concave down. Yeah, Sebastian sees it, and you know, so you know, okay, well then there have to be, let's see, 1, 2. Let me just see here, 1, 2, 3, 4, 5 inflection points, right? There have to be 5 inflection points. And the question is, what are those inflection points? Well, the inflection points are where your second derivative equals 0, right? The inflection points are where your second derivative equals 0. And so what they do here is if we go here to figure 17, they find the second derivative, okay, using calculus. So you have to use calculus, right, to find your first and second derivatives still. But they graph the second derivative, and you can see let me just see here. I'm looking at where the second derivative crosses the x-axis. That's where the second derivative is 0. And I'm seeing 5 places on this graph where it does that. Okay, 1, 2, 3, 4. Well, and the origin is also an inflection point, but I'm seeing 5 places where it does that. And so, you know, basically that's really, you know, I don't want to make this section harder than it is. You know what I mean? When you first look at the section, you're thinking, man, this looks kind of hard, but it's not really hard. It's just, you know, you have to take your first and second derivatives of your functions and then graph the first and second derivatives, find out where the first and second derivatives equal 0, and then distinguish between where the function is increasing, decreasing, concave up, concave down. I mean, it's really that simple. Are there any questions on that? Just, you know, in general? It's only for section 4.4 that you use the calculator. But of course, the derivatives you have to work those out by hand. But you know, we have to have the ability to work with more complex functions. Right? As scientists, we have to have the ability to work with more complicated functions, and that's what 4.4 gives you some guidance on. Okay, so all right, are there any questions on that? On section 4.4? So I didn't really, I mean, I just went over examples in the book. I think for that, the examples in the book are excellent. They're as good as anything I could write down on paper, so I'm just content to, you know, cover section 4.4 that way. Examples are very good. Are there any questions? Maybe give a thumbs up if you're okay with 4.4, at least the idea behind. All right, Joe's good. Nicholas is good. Wonderful. Zoe's good. And Joe, John, Ian, great, wonderful. Rodrigo, excellent. All right, well, let me go ahead and stop the recording.